Alright, we're going to start off the second part of our Vectors and Projectiles unit. Officially this is part of projectiles, I guess, but we're really going to start off with a review of some of the kinematics. And by review, you probably did this in grade 11. You for sure did it if you were with me. You may have done it if you were with grade 11 with somebody else. So first of all, a definition of velocity. So the velocity, I guess in words you could say, is how the rate at which displacement changes, or position changes I should say, with respect to time. So it would be, I often say, delta d over delta t. Officially I'm going to put the little vector symbol over top of there and the vector symbol. So it's the rate at which your position is changing. It's the change in position. Delta d, change in position, divided by the change in time. Now this is a good definition here. You can use this formula for the constant velocity. It's good for constant velocity. It's also good if you're using average velocity. The problem is if you don't, you want to stay away from this formula when your velocity is changing. Okay, so maybe put a little note here. When velocity is changing, that's when you start want to be thinking about acceleration. So acceleration is not how position is changing. Velocity is how position is changing with respect to time. Acceleration is how velocity is changing with respect to time. So again, this is a vector and that's a vector. So you'll notice that the delta v, because velocity is changing, the change in velocity divided by the change in time. Velocity is the change in position. Let's do one example here and we'll fill it out below here. Let's say we've got a car that is moving at a constant velocity. Okay, so let's say we'll start off, we'll make a dt graph here. So d for position in meters, time in seconds, and let's say, let's keep it easy, let's say it starts at 0 and is increasing here, is moving along, and say after 5 seconds, has gone 20 meters. Okay, so the whole time, I guess if I could kind of click a 1, 2, 3, 4, 5. If those were even, if this was a 1, then what would this be here? Well, if it's going 20 meters in 5 seconds, then it goes 4 meters, assuming at a constant velocity. So, and we'll even say it continues to move here. All right, so this would be a dt graph. Now, if we wanted to figure out velocity from it, we would look at the slope of that graph. So the slope of that velocity is going to be equal to the rise, which is the change in d, divided by the change in time. So change in means like how much has it gone up by. So we could pick any 2 points, but we may as well pick the beginning and the end. We could say, alright, so here is the delta d part is equal to, well, how much did it change by? It went up 20. In other words, you could say 20 divided by 20 minus 0 is another way of looking at it. How much time went by? Well, this is how much time went by, and it looks like 5 seconds went by from the beginning to the end. 20 meters divided by 5 seconds, it's going at a velocity of 4 meters per second. Okay, so it works great. So that's an example of constant velocity because it's in a straight line. So now let's look at what the exact same VT graph would look like. So if I did a VT graph of that same car, so now it's a VT graph. It's going 4 meters. This is a straight line. In other words, the slope is constant. If the slope was changing, this would be a curvy line. So really, I just put a 4 here, and the units here are meters per second, and it's going, at the end of 5 seconds, it's going at a constant 4 meters per second the whole time. So this car, same car. This is a dt graph, a position time graph. Here's a velocity time graph. It's going at 4 meters per second the whole time. So how could we figure out the displacement if we went backwards? If I covered up this stuff over here and I just gave you this graph and I said, how far did it go? Well, so the displacement is equal to the area under the line. So in other words, we would have to figure out the area in here. Okay, and that area right there. And that area is a rectangle, and that area would be, well, the height would be this, the height would be 4, and the length would be 5. So this area would be 4 meters per second multiplied by 5 seconds, which would be equal to 20 meters. And that is indeed how far it went at the end, right? It went 20 meters. So the area under the VT graph is displacement. And the slope of this one, well, what's the slope of this? Well, it's a flat line. So the slope would actually be, the acceleration is equal to the slope, which is the change of delta v, the change in velocity divided by the change in time. Well, it started at 4 and it stayed at 4 the whole time. So in fact, in this case, the change in velocity is 0. And 5 seconds later, 0 divided by 5 is 0 meters per second squared. Okay, so at the end of the day now, if we were to make an AT graph of this same car, it would be 0 all the way through. Okay. That's how it would look. The area under the AT graph would be equal to, actually, it would be the change in velocity, not quite velocity, but the change in velocity. Okay, and there is no change in velocity, is there? Stays the same the whole time. So just to get another way to write it down really quickly, if you got a DT graph, the slope of that tells you the VT graph, and the slope of that tells you acceleration. Okay, if you go the other direction, the area under the line gives you, well, not quite VT, but it tells you how the velocity is changing, and the area under the VT graph tells you this way. All right, so why is the VT graph most useful? Because if you got the VT, you can find the slope of it to find AT. You can look under the area under the line to find out how displacement, how position has changed. Okay, so you can use it. So what we're going to do is, we're going to, in all our questions, we're going to sketch VT graphs. Okay. I'm going to give you one more example of this area under the line. So let's say if we had a VT graph, a velocity time graph. Oh, I don't know, let's say started like this and then it went like that. How would you find the area under the line? So you could kind of pick a vertical part there. So the area under the line, if I'm zooming in here, the area under the line would be this yellow zone here. So it would be this shape and that shape over there. So just to let you know about how to figure out that area, because I think there's a couple examples like that where it comes up. Alright, let's do our first one here. It says, example number 1, a car is traveling at 45 kilometers per hour when it begins to brake, taking 4 seconds to come to a complete stop. So what we're going to do in all these questions is we're going to draw or we're going to sketch at least a VT graph. Okay, so I think that we're not going to be going at a negative velocity, so I can just limit my work to the first quadrant here, so it's all going to be positive. So this is velocity, and I'm going to, should I change this to kilometers per hour? You know what, how about if we go, and I'll do this in meters per second. And I'll show you how to change this, and this will be time in seconds. Okay, so the first thing we want to do is, if it's going 45 kilometers per hour, if we want to change that 45 kilometers per hour into meters per second, I'm going to divide by 3.6. You might just remember that from our from grade 11 course. So hold on, I'll find out what that is. And my calculator says it is 12.5 meters per second. So I'm going to start off at 12.5. Whoops. I'm going to start at 12.5 meters per second, up there. And then it says it begins to brake, taking 4 seconds to come to a complete stop. So in other words, my line starts here, and that's supposed to be straight, and it ends over there. Okay, so the first part, part A, is find the car's negative accelerations. This gives you a hint that the answer should be negative by saying negative acceleration. So again, how do you find acceleration from a VT graph? Oh, from a VT graph you find acceleration by doing the slope. And actually the definition is, acceleration is the change in velocity, which will be the rise, divided by the change in time, which will be the run. So the change in velocity from the first point to the end point is it goes down 12.5. So A is going to be equal to delta V over delta T. The change in velocity will be negative 12.5 because it starts at 12.5 and ends at 0. And how much time goes by is 4 seconds. So I go 12.5 divided by 4 and I get a negative 3.125 meters per second squared. Remember the units for acceleration is meters per second squared. Part B is to find the displacement. So the displacement here is going to be equal to this area under the line. So that will be that area there. So area under line. So that's going to be the form of a triangle, base times height divided by 2, where the base is 4 seconds and the height is 12.5 meters per second divided by 2. 4 divided by 2 is 2. 2 times 12.5 is 25. Note what happens to the units. Seconds times meters per second means that the seconds cancel each other out. I get 25 meters as my answer. Okay, let's try example number 2. A car accelerates uniformly from rest. So if it's going uniformly, that means it's going to be a constant acceleration. So that's going to tell you two things. Number one is once we get to the big 5, that means that we can use those because the big 5 are only for constant acceleration. It also tells you that on a VT graph, it's going to be a straight line, right? So it's going to be not a curvy line, a straight line. A car accelerates uniformly from rest at the rate of 2 meters per second squared for 6 seconds. So I'll just keep track here. My acceleration is 2.0 meters per second squared. And how much time goes by is 6 seconds. And then, okay, so that's part number 1. And then it maintains a constant velocity. So, segment number 2, it goes a constant velocity. So I could even say A equals 0 for a little while, constant velocity, for 30 seconds. So this is like delta T1, and then delta T2 is 30 seconds. Finally, the brakes are applied and the vehicle slows down. So this is part number 3. And the vehicle slows down at a uniform rate and comes to rest in 5 seconds. So this one, delta T3 equals 5 seconds. Alright, so let's see if we can sketch. We won't have all the numbers, but let's see if we can sketch some type of a VT graph here. And again, it goes in a positive direction the whole time. I don't think it goes forward and then it goes constant and then it comes to a rest. So at the beginning it is goes for 6 seconds and then 30. Okay, so we have a 6 here for time. And then another 30 seconds, so over here will be 36. And then in another 5 seconds over here it will be 41. So during the first part, it's going to be accelerating at 2 and a constant acceleration. So it's going to be increasing. I'll just put a dot somewhere here, so it'll be increasing up like that. So this 2 here means that this is the slope, right? I'll put a little note here. Slope equals 2. Okay, so if it rises 2 meters per second every second, then what will this value be up here? What at the end of 6 seconds, it'll have gone up to 12 meters per second. Okay, or we could even say, so A is equal to the delta V over delta T. We could think about it like that. We could say, therefore, 2 is equal to how much the velocity changes by, and there is 6 seconds going by. So to solve for delta V is equal to 12. So in other words, if we started at 0, we must have got up to 12. Okay, so we got up to 12 here. I'll erase my other work just so that we can see stuff. So we got up to 12 here. Now we stay at a constant velocity for 30 seconds. Right? And then it says it slows down at a uniform rate, coming to rest in 5 seconds. So at the end it goes all the way down to there. Alright, so first of all, find the maximum velocity of the car. Well, I guess we did that already. We said it's 12 meters per second. And then it says find the total displacement. So to find the total displacement is to find this total area. So to find that total area, probably the easiest way is to block it off into 3 different segments, right? So I'll call this one A, and then B, and then C. So the area for A is going to be, it's a triangle, base times height over 2. The base is 6. The height is 12 divided by 2. So that's the same thing as 3 times 12, which is 36 meters. B is a simple rectangle. Now be careful, it's not 36, but rather this distance here is 30, right? 30 times 12, I'll say length times width. 30 times 12 would be 360 meters. And then during C, it's again going to be a triangle, base times height over 2. The base again was 5, and that height was 12 divided by 2. If I do 12 divided by 2, it's 6. 6 times 5 is 30 meters. So my total displacement will be 36 plus 360 plus 30, which would be equal to, let me see here, 6 to 426 meters. There we go. All right. Checking out example number 3 here. A ball is thrown straight up. It leaves the player's hand with a velocity of 30 meters per second up. Oh, sounds like I could start my VT graph already. So here's my VT graph. Here's V. Here's T. It starts at 30. Way over here, 30. This is in meters per second. This is in seconds. Okay. If it accelerates at minus 10, in other words, the slope here is going to be minus 10 as it rises to maximum height. Okay, so it's going to be going. Okay, so let's think here. If this slope it decreases by 10 meters per second every second, how many seconds go by? So it must be 3 right here. Okay, or we could say, all right, well, A is equal to how velocity changes divided by time, right? If A is minus 10 and the velocity is going to go from 30 down to 0, that means the change in velocity will be minus 30. What's delta t have to be? So if I do my math on there, I'll get a delta t of 3 seconds. Okay, so the question A is the time to reach the maximum height. 3 seconds. And then it asks, oh, hint, at maximum height the velocity will be 0. So that's what we did. So it's kind of strange to think about. This is the VT graph, and what it looks like is the ball is going up like this and then stops at the highest point. So here it's going upwards at 30 meters per second. At the top, it stopped. Find the maximum height reached. So the maximum height, really what they're asking for is what's the displacement, right? So again, it's going to be this area, and it is a triangle where the base is 3, the height is 30, divided by 2. So 3 times 30 is 90, divided by 2 is 45 meters. Okay, moving along, we got example number 4, and is that our last one? Yeah, example number 4, and then after that you got a little bit of homework to do. Okay, example number 4 says a driver hits an icy section of the road. If the car moves 60 meters in 25 seconds before coming to a stop, find the car's initial velocity. Okay, so it moves 60 meters. So if I'm making my VT graph, this is going to be the area, right? The displacement is the area on a VT graph. It goes 25 seconds. Here's the time. Here's the velocity in meters per second. So it is moving to begin with, and then it comes to stop. So in other words, it started some value here, and then it ends over there. So this is the part that I don't know. Okay, but this area inside, I get to color. The area inside there is 60 meters. So I'll set this up. I'll say the area of that triangle, which is base height divided by 2, is equal to 60 meters. So 60 is equal to, now the base is 25. The height I'm really going to find out, divided by 2. So I will multiply both sides by 2. I'll get 120 is equal to 25h. I'll divide both sides by 25. So h is going to be equal to what? 4 4/5, so 4.8. I think I got that right. And so the units really for this height here, this is going to be 4.8 meters per second. So again, in every one of these questions, I drew a VT graph. And I used the principle that the slope of the VT graph, on a VT graph, the slope is equal to acceleration. Okay, so in other words, A is equal to the rise, the delta V, divided by the run. So that's the first principle that I used. And the second principle that we used, number 2, is that the area, now I say area under the line, but you know, between the line and the x-axis is equal to the displacement. So looking over the sheet, in bold are the answers for each question. Let me give you a hint about, let's say, okay, let's look at number 3 for a second here. So for question number 3, it's given in kilometers per hour. And you'll notice that the answers are in meters per second squared and in meters. So step 1 would be convert this. Okay, so 36 kilometers per hour. And if we want to divide by 3.6 to change to meters per second, I'll get 10 meters per second. Okay, and then 54 kilometers per hour divided by 3.6. What is that, 15? Yeah, 15 meters per second. Okay, so just to help you with this one, it says it starts at 10 meters per second, and then it ends up at 15 meters per second. So 10, 15. So here's my velocity, here's my time. Okay, and it goes for 5 seconds. So in this one, going like this. Okay, so just a reminder, then you need to find the area. When you find the area, a lot of people just find the area of this triangle, but you really want to find out the area of this whole piece here. Okay, so really it'll be the area of a triangle and a rectangle on the bottom, so you might want to chunk it into 2 pieces. Okay, so alright, and that's good. Okay, try those out, and I think there's is there just the one? Oh, I think I'll probably be giving you 2 sheets. Okay, we'll see you in class.